So, good morning. So we will continue with lecture 37, and we will go to multiple random variable case. So let us consider n discrete random variables. So as usual, we start with the discrete case, and we have here n discrete random variables. Then in that case, for the multiple random variable, the joint PMF will be denoted, will be defined like this. So this is the usual notation that just now extended to n random variables. And for the continuous case, we know that we don't have the PMF, but rather we have the PDF. So PDF notation will be this, and in that case, the probability we know is given by this integral. Okay, so that's how we define the joint PMF for the n random variable case, and then we also define how to compute the probability in the continuous case, and we integrate it over the area A, okay, which is defined by this. Okay, then we can also define the marginal random variable of xi, and this can be obtained by integrating out all other xj's. So if I want marginal with respect to xi, then I can integrate with respect to all other xj's. So it's just that the notation becomes a little bit more here. So for example, if I want to compute margin with respect to x1, then I will integrate out with respect to x2, x3 up to xn. Okay, so I just leave out x1. Okay, and joint CDF of n random variable is again, as usual, it's defined like this, where x1 less than equal to x1, x2 less than equal to x2, and so on. So let us see an example in the multiple random variable case. In other words, here we have three random variables, and the joint PDF is given to us, and this is the joint PDF. X, Y, Z are the three variables here. Now find the constant C. Again, since it is a PDF, the integral must be equal to 1. In this case, again, the triple integral must be equal to 1. And then the marginal PDF of X, let us say if I want to find, then I have to integrate this out with respect to Y and Z variables. Okay, so we can actually do this as a sample example for the multiple random variable case. So the first question is find the constant C. So to find the constant C, we have 1 is equal to, and we do minus infinity to infinity, then minus infinity to infinity. So there are three integrals now because there are three random variables, and f, x, y, z, and then x, y, z, and then dx, dy, dz. Okay, so it's a matter of integration. So the limits of the integration will be given by these range values here. So these are from 0 to 1. So let us do that. So 0 to 1. So 0 to 1 is also 0 to 1 is also 0 to 1. And we have the PDF is x plus 2y plus 3z. C times x plus 2y plus 3z, and dx, dy, dz. And this, if we integrate out, so we have to do this one by one. Okay, so if we integrate out x, so in this case will be like x squared by 2, and then 2yx. So let us do that. So 0 to 1, 0 to 1, and we integrate out the x. So this is 6 cx squared by 2 plus 2yx plus 3zx. Okay, and the remaining terms are now integrated with respect to dy. Okay, but here I have to put the limits of the integration after integration. So 0 to 1 dy dz. So this is 0 to 1, 0 to 1, and then if I put 1, then we have c half. Okay, so c was a constant which was outside, so I can put it outside, and then I have half plus 2y plus 3z. Okay, so this is the value we get after integrating with respect to x, and then similarly I can do for integrate with respect to y, let us say now. So we have c and then half y plus 2y squared by 2 plus 3zy, and then what is left is dz here. So now, yeah, so again, we have 0 to 1. So if we do this, then this is 1 plus half is 3 by 2, 3 by 2 plus 3z. So 0 to 1 c times 3 by 2 plus 3z is what is left. And then similarly, it's a matter of integration only, right? So so now we have okay, so let us do the final step where we have 3 by 2 c z plus 3 z square by 2, 0 to 1. So this is so if we put 1 here, right? So if we put 1 here, so 3 by 2, 3 by 2, so it's like 2 times 3 by 2, so it will be 3, so c times 3. Okay, so this implies that c will be 1/3. Okay, we started from 1 here. So that's how we find the constant. And then what was the second question? So find the marginal PDF of X. So to find the marginal, according to the definition, we have to integrate out with respect to Y and Z. Okay, so let us do that. So the marginal with respect to X will be minus infinity to infinity, minus infinity to infinity, and then fxyz, xyz, and then since I'm computing with respect to X, I have to integrate out dy and dz. Okay, so if we do that, then well, it's a matter of integration again. So it will be, yeah, so here I have to do it. So 0 to 1 and 0 to 1. So these are the integrations, and then x plus 2y plus 3z dy. And yeah, so you can solve for this to get this answer, right? So it will be x will be remaining here, right? So it will be a function of x eventually. Okay, so we can also talk about independence of multiple random variables, just like we have done independence for 2 case. So these are just extension of the two case. Now we have a general n random variable case. So they are independent. Again, the definition is simple. The CDF with respect to x to xn will be the product of, and if x1, x2, xn are discrete, then they are independent. Then they are defined to be independent if the PMF values are the product of the individual PMF. The joint PMF is product of the individual PMF, and in the continuous case, we know that we talk about the PDF. Okay, in the discrete case, these are PMF. Okay, so in the continuous case, the PDF should be the product of the individual PDF. If x1, x2, xn are independent, then obviously this relationship will hold either for it holds regardless of whether it's continuous or discrete. Obviously, it follows from the definition itself. So we can write things like this. Okay. Variables x1, x2, xn are said to be independent and identically distributed if they are independent. Okay, so there is a new term here, independent and identically distributed. Okay, so in the definition itself, you know that it has to be like these must be independent, and identically distributed means that they are coming from the same distribution. Okay, but instead of saying that, we say that they have the same marginal distribution. Okay, which actually implies that they will have they follow the same distribution. So more precisely, we say that x1, x2, xn are independent. IID if they are independent. So, by the definition of independent in the previous slide. And furthermore, they have the same marginal distribution. So these are the marginal distributions, and they must be exactly the same. Okay. So one example of this could be is that if we flip the same coin n times and record the outcome, then those. So this is the outcome for the first flip, and this is the outcome for the nth flip. So these x1 to xn are IID in this case because they are independent. The coin flip are independent of each other, and they are coming from the same distribution because it's the coin toss itself. So they follow the same Bernoulli distribution, right? So this is an example, and then yeah, so you can verify that although we have not explicitly mentioned that the mean and variance has to be same, but given the assumption that they are independent and given that the marginals are equal, you may actually prove that they will satisfy the same mean and variance. Okay, so that's the consequence of that. Okay. We can also define expectation and variance for multiple random variables. So let us say y is sum of x1 to xn. Then if we want to compute the expectation of y, then if due to linearity of expectation, it will be sum of the expectation. And we recall for the two variable case that the variance of x1 plus x2 is given by variance of x1 plus variance of x2 plus 2 times covariance of x1, x2. This is the formula we derived previously. So what we observe in this case is like variance with the sum is like this, but then there is a pair term as well. Okay, so there is a pair term as well. So how we will extend this definition to the sum of n random variable case? Okay, that's the question. So in the general case where we have sum of n random variable, this is the formula that holds. The variance of the sum is the sum of the variance plus the pairwise terms. Okay, so this is something you can actually prove this. Okay, by induction, let us say. So you can try to prove this. So since you have more terms, you will have more cross terms here, right? So basically you will sum over all this where I is less than equal to j. Okay, less than j. Okay, so so this is the definition or the computation for the n variable case, okay, which can be actually proved actually. Okay, so if x1 to xn are independent, then the variance will be sum of the. So this is something we have done for the two variable case. So if x1 and x2 are independent, the variance of x1 plus x2 is a variance of x1 plus variance of x2, and this is because if they're independent, the covariance term goes away, right? So the same thing happens here. So here we are talking about n random variables and they are mutually independent. So those cross terms won't be there anymore. So this is also we have proved before. Okay, so the covariance of xy is expectation of xy minus expectation of x, expectation of y. So this is something we have done. So if they are independent, then they and these terms are the same and they will cancel. So this is easy to verify. Okay, so n people sit around a table where n greater than 5, each person tosses a coin. Anyone whose outcome is different from his or her two neighbors will receive a present, and so on. Okay, try this as an exercise maybe. Okay, so I'm going to skip. Okay, so the PDF of sum of multiple random variables. So how we can find the PDF for the sum, right? So if in the two variable case, if you recall in the previous classes, we saw that it's given by the convolution. Okay, so the fy, the joint, so this is x1 plus x2, the PDF, the joint PDF is given by the convolution operator. So this is called convolution. Okay, or in more precisely, this is how the convolution is defined, minus infinity, and so on. Okay, so the question is, this was for the two variable case, sum of x1 plus x2. What will happen if we do it for the general case? Well, you have to do a generalized convolution like this. Okay, so you can just extend this to convoluting multiple PDFs. Okay, so for the sum, yeah, you have some idea of let us say you have some module that does the convolution, then you can try to do that using the convolution operator. So it will be computationally difficult, obviously, because if n is big, then yeah. Definitely. So what I have shown so far are the multiple random variables, right? So what we can do as a next step is, so what we have discussed so far is x1, x2, xn. Okay, so this is the multiple random variable case, but the thing is like I can also make them into a vector. So vector, and then I collect all those in a one vector. OK, and similarly, I may have another vector which contains another set of n random variables. So I may actually extend this to vector of random variables. So that's the next concept we want to. So we started from single variable, double variable, and then now we are talking about multiple random variable, and now we are going even more, even further ahead, and then we were creating now vectors of random variables. So how do I define this? So when dealing with multiple random variable, it is useful to use a vector and matrix notation, obviously. So this helps using a compact notation and tools from linear algebra. Let x1 to xn be n independent random variables. Okay, then the random vector is defined like this, as I said. So if x is a random variable, random vector, and the components are random variable. OK, so expectation again due to linearity will be component wise expectation. So if I want to compute expectation of a random vector, then it will be expectation components which are the random variables. So we call x a random vector in this case, and ex is expectation of a random vector, obviously. So CDF is again for the random vector can be defined like this, because I treat this as a collection of n random variables. OK, so so I can use a shorthand notation x instead of writing this long notation x1 to xn. So this is now a vector x. OK, and with components x1 to xn, which are n random variables. So yeah, so it's the usual definition here. And if x is jointly continuous, again, it's just about the notation now. So instead of writing this, I can write this as one vector. And then, yeah, I can, which is defined to be like this. OK, so this is also seen as a vector. So this small x is seen as a vector x1, x2, xn, and then we have a capital X with the components capital X1, capital X2, capital Xn. So these are like shorthand notations. OK, shorthand notation. So OK, so we have extended this, and of course nothing stops us from also considering a matrix now. Matrix of random variable, right? So whose elements are random variables. So for instance, if I have a matrix M like this, whose components are now random variables, then I can talk about expectation of M to be a pointwise operation on the individual components of the matrices. Here M is called a random matrix, okay, because it's a matrix, and expectation of M is the expectation of a random matrix. Okay, this is the way we define. Remember that expectation makes sense only for a random variable, but we have extended the definition to the matrices. But in principle, it's expectation of the random variables inside. Okay, so also if x1 to xk are k dimensional, are k n dimensional, are k, okay, there are k random variables and each of them are n dimensional, then so remember each are now random vector now. Okay, so they are n dimensional random vectors. So again, we can like extend the definition in the same way due to linearity. Okay, so I can treat these as a vector. Okay, so each of them as a vector. So again, I can expand them like this, like a sum of the expectation of the sum of the random vectors will be sum of the expectation of the random vectors. Okay, so it's just extends. So variance of sum of random variable. Okay, so variance of multiple random variable. So if so this is something we have denoted before, and okay, I don't know why I'm writing this. I have already mentioned this before. Okay, what matters is correlation and covariance. So let us see how we can extend the definition of correlation and covariance. For a random vector x, the correlation matrix Rx and covariance matrix Cx. Okay, so what is this, right? So this is expectation of x transpose. So that's the correlation. Okay, so correlation is defined to be like this. But now that since x is a vector, so we have to multiply that out. Okay, so we have to multiply that out. So I think I'm missing expectation here. So this inside term is just xx transpose. Okay, So X is so it's like this, right? X1, X2, Xn. Okay, and this is the outer product, right? So like this, and then X1, X2, Xn. So if you multiply this out, column times a row vector, so it's possible, right? So X1 square plus X1, X2, and then X1, Xn, and then X2, X1, X2 square, X2, Xn, and then Xn, X1, Xn, X2, and then Xn, Xn. Okay, so this is the outer product. So this is called outer product. And if you multiply row times a column, then it's called inner product, right? So this is the outer product of the random vector with itself. Then this is the matrix we get, and this is the matrix which is written here, and we have to do the expectation of these. Okay, so expectation will just go inside of the, and it will do for the individual term. Okay, so okay, I think there is a mismatch here. Okay, so these terms, this guy, I must put it here, X1, Xn. Okay, so and covariance matrix is defined to be like this. So covariance is so these are not cross. Okay, these are just, so there is also concept of cross covariance, cross correlation, right? But this is this is with itself, right? So that they are called covariance correlation. So this is like X minus EX transpose, X minus EX transpose, X minus EX, and X minus EX transpose. Okay, so it's like with itself. It's with itself. So, and this is what we will get. Okay, so if we apply the expectation and so on, so you just multiply this out, and then you take the expectation. So, and then you will figure out which term is corresponds to the variance, which term corresponds to the covariance, and so on. Okay, so this is the definition for the correlation and covariance matrix. And this is the relationship that holds for between the correlation and covariance. Okay, so this is something one can prove. And if y is equal to ax plus b, and a is m by m and b is m dimensional, then cy can be written as a cy can be written as a cx a transpose. Okay, so I think these are the things like one you can try to prove this. Okay, I don't think I have to do. So you can try to do this these proofs. Okay, so it should be easy enough. Okay, so let us see example of correlation and covariance matrices. Let x and y be jointly continuous random variable with joint PDF given by this. And then we have formed a vector now. Okay, so u is xy, be a random vector. Find the correlation and covariance matrices of u. Okay, so find the correlation and covariance matrices of u. So how will you like go ahead with this? Right. So for correlation and covariance, what are the things you need? Right. So yeah, it's defined to be expectation of correlation and covariance. This is the way it's defined, right? So I'm supposed to do this guy, right? This expectation of x squared. Since I have a two vector of length 2, I will get a 2 by 2 correlation matrix, right? So I am supposed to find these terms, right? So these are the terms I'm supposed to find in this example, because I have a vector u whose components are x, y. So for us, x1 is x and x2 is y. Okay, so let us do this example very quickly. So find correlation and covariance matrices of u. So let us see how to do this. So the first thing is like I need the marginals, okay, because I need to compute the expectation, right? Again, I'm sorry, I have to go back. Okay, so I need to compute expectations like this with respect to x1 square. So I need a marginal with respect to x1, right? and I need marginal with respect to x2 for this guy. Okay, so let us see how the first step would be to compute the marginal. Okay, so solution for this would be we first find the marginal. Marginal PDFs of x and y. So what do we have? So fxx, the marginal we have to compute. The joint is given to us 3/2 x square plus y, 3/2 x square plus y. Marginal with respect to x, so I integrate with respect to y, and the range of integration are 0 to 1, 0 to 1. Okay, so this will be 3/2 x square plus half. Okay, so that's the result of the integration. Similarly, we have marginal with respect to y, so fyy is 0 to 1, 3/2 x square plus y, and this is with respect to x. Now we have to do, so this will be yeah, so result of integration in this case will be y plus half, right? And so this is for 0 less than y less than 1, and this is for 0 less than x less than 1. Okay, so so now to compute the, so we recall that the correlation matrix, right? So correlation matrix, which is the R, is given by expectation of x square, expectation of xy, expectation of yx, and expectation of y squared. Okay, we are supposed to compute, right? So once we have the marginals, right? So we can actually go ahead and compute the expectations x square and y square and so on, right? So expectation of x square will be minus infinity to infinity x square and the PDF of x, right? So marginal with respect to x, and then dx. So x actually goes from 0 to 1 and x square, and marginal with respect to x is 3/2 x square plus half. Okay, and dx. Okay, and similarly you can compute expectation of y square. So similarly we can compute expectation of y square. Okay, and expectation of the thing here. Now we need the double integral, right? So 0 to 1, 0 to 1, because x and y between 0 to 1, and then the joint and xy term, so xy, because this is function of that, and then the joint PDF, which is 3/2 x square. So this was the joint 3/2 x square plus y, and then dx dy. Okay, so it's a matter of computing this integral, right? So once you have these terms, you can now go ahead and expectation of xy and yx won't change anything in this case. Okay, so there is no, so they will be same actually. Okay, yeah, so that's it. So you can compute the correlation and covariance. Covariance of xy. So this was expectation of xy minus expectation of x, expectation of y. Again, you have computed this before, so this can be computed. So the so covariance of x, so correlation matrix. So covariance matrix, I'm sorry, yeah, covariance matrix. Covariance matrix was what? Covariance matrix was so CU, right? So CU was expectation of x minus expectation of x, right? And then x minus expectation of X again transpose. Okay, so here I have to be a bit careful. Okay, so 1 second, I did a, yeah, so here I mean U, right? Okay, so let me, because I'm computing U, right? So this is expectation of U minus expectation of U, and then U minus expectation of U transpose. Okay, so if you multiply this out, then what we found out is it will boil down to, so after expanding U and so on, so it will be variance of X and then covariance of XY and then covariance of XY or YX is the same thing due to covariance property, we know that, right? And variance of Y. Okay, so this is something that can be computed again because you have the expectation values and those will be needed to compute these covariance terms and so on. Okay, anyway, so this is fine. So we have the following properties for the covariance matrix. Covariance matrix CX is symmetric. Okay, and the covariance matrix CX is also positive semi-definite. Okay, and the covariance matrix is positive definite if and only if its eigenvalue are larger than 0. The covariance is positive definite if and only if the determinant of the covariance matrix is greater than 0. Okay, so these are the properties. Basically, these are properties of the linear algebra also. The last two are nothing but the linear algebra property. So if someone tells me that it's positive definite, then obviously eigenvalues are larger than or equal to 0. So covariance matrix is a symmetric matrix. Why is the case? So if we see the covariance matrix, we have to go all the way back. Yeah, so this is the definition of the covariance matrix. Okay, why is this supposed to be symmetric? Because of the covariance property of the two variable case that we have seen, that covariance of XY is equal to covariance of YX. So this is something we know. Okay, so this is something we recall. So if that is the case, then these guys, IJ entry is equal to JI entry, right? So that's the definition matrix, right? So covariance matrix is a symmetric matrix. That is clear. Okay, because covariance of XY is covariance of YX, and then the another thing was it's a positive definite, right? So why covariance matrix would be a positive definite? Right, it is symmetric is fine, but why it has to be a positive definite? So what is the definition of positive definite matrix, right? So what do we mean by a positive definite matrix? So if you recall the definition of positive definiteness, so positive semi-definite, right? So a matrix is, so recall the definition of positive definite. You can try to prove this. It's not be if you recall the definition of positive definite, then what was that? A matrix A is positive definite. So let us say it's PD. If what do we have? If the following holds, right? X transpose AX. Okay, so if we talk about, let us define semi-positive definite. SPD. Okay, if X transpose AX is greater than or equal to 0. Okay, for the semi we have greater than or equal is also allowed. If you talk about only positive definite, then it's like strictly greater than 0. So for all X not equal to 0, for equal to 0, obviously this will be equal to 0 only. So this is the definition of a semi-positive definite matrix, and we also assume A to be symmetric. A symmetric. Okay. So basically the non-symmetric part doesn't really matter. Okay, so usually we define it for the symmetric matrix. Okay, the positive definiteness. I don't want to go into the detail of that. Okay, that's so let us. So this is how I defined this for you. So symmetry is already given to you for the covariance, and it is claimed that it is positive semi-definite. Okay, so in other words, if I do this, obviously X is fixed. Okay, so and in our case, like even Cx is fixed, right? So the question is why it should be greater than or equal to 0, right? So I can leave you with a small hint, and then you can try to fill the gap. Okay, so why this will be the case is because remember the covariance matrix Cx is defined to be expectation of x minus expectation of x and x minus expectation of x transpose. So you see the form of this, right? They are matrices, right? So they are matrices. So I can, let us say I substitute this by some, let us say Z matrix, and this is also Z matrix. So this is of the form Z transpose, right? So this is like expectation of Z transpose, right? So Z transpose. Okay. Now what is the nature of this guy, right? This is a matrix. So let us define this to be the matrix A, right? So can you what can you say about this matrix? Is this symmetric? Right. So is this matrix symmetric? It is symmetric, right? Because Z transpose. So it is symmetric, right? So symmetry is possible because A transpose is Z transpose. Transpose of this will be again Z transpose, which is A. So A transpose is A. So this implies A is symmetric. Okay. And another thing I claim here is that A is positive definite. So SPD. Then for that I have to claim this, right? So for any non-zero x, I must satisfy this. So why this should be the case, right? So let me try to do this here. So I multiply this with x non-zero, some non-zero Z transpose. So like I multiply this with x transpose AX, right? Now, is there any guarantee that this has to be greater than or equal to 0, right? Then I can claim that Z transpose is actually Z transpose is actually positive definite, right? So how can I guarantee this, right? What do you suggest? Like what is this guy going to be greater than or equal to 0? Obviously x is non-zero. X equal to 0 will be equal to 0. So what should I do here to ensure that this guy must be greater than or equal to 0, right? So what do you think? What should I do here? Can you tell me in the chat why it should be greater than or equal to 0? So what do you think? Any idea why? Okay, so let me do this. So how can I write this? I can rearrange this, right? So this I can write this as ZX transpose. Okay, is this correct? X transpose. So I have to do transpose here, right? Z transpose X transpose Z transpose X. Okay. Now this is the same thing transpose with itself, right? So this is the norm, right? So this is the norm of Z transpose X, right? So this is the norm of Z transpose, like the two norm, and the norm is always greater than equal to 0, right? Norm is always greater than equal to 0. So that's done, right? That's the property of the norm, okay, from linear algebra. So this is true for all this. So you are taking expectation of right, this guy, right? So if you multiply this by x from outside also, okay, but then x, due to linearity of the expectation, you can bring it inside, and then due to linearity of the I've shown is Z transpose is positive definite inside term, right? I've shown that this is positive definite, but you are actually have to show expectation of that is positive definite, right? So you have to use the linearity expectation and so on. So what I have to show is actually X transpose expectation of Z transpose X is greater than equal to 0. What I have shown is this guy is greater, is always regardless of the Z, regardless of what Z you choose. Okay, that's the important point. Regardless of what Z you choose, Z transpose is always going to be symmetric and positive definite. And okay, so I have proved this result, but then because x is a kind of a fixed value here, so you can bring this x inside. Okay, so you can bring this x inside due to linearity. Okay, and also you can bring x inside from this side also. Okay, and then you are in some sense it's like taking expectation of a positive value, right? So average of a positive value must be positive only, right? Because the inner term we proved that it's positive anyway. So this is the minor things you need to change to prove that this will be a positive definite also, or semi-positive definite. And then the third property that we have, third and the fourth property we have, is that eigenvalues are larger than 0, right? So if a matrix is positive definite, so here we are talking about strict positive definiteness, right? So X transpose AX is greater than 0, okay, for all X not equal to 0. So A is positive definite, it implies, this is the definition of that, not implies, but this is the definition. So it's saying that eigenvalues are larger than 0, right? So if lambda is an eigenvalue of A, eigenvalue of A, so then this implies A u is lambda u for some u eigenvector. And then this result, A lambda is any arbitrary eigenvalue of A. Then what it is claiming is that lambda must be larger than 0. Okay, and you are supposed to use this property, right? Now u being an eigenvector, u eigenvector implies u must not be 0 because eigenvectors are never 0. So then you take the x to be then you take x to be u itself, right? So we have u transpose AU. This is supposed to be greater than 0, right? Okay, because A is positive definite. So, but u transpose AU is what? So AU is lambda u, right? So this implies u transpose lambda u is greater than 0. This implies lambda times norm of u is greater than 0. But this is like always a positive quantity. Okay, so I can divide by this. So this implies lambda is greater than 0. And lambda was any arbitrary eigenvalue, right? So this does imply that eigenvalues are larger than 0. The covariance matrix is positive definite if and only if the determinant is greater than 0. Obviously, determinant is product of eigenvalues, is product of lambda I, right? So, but lambda I are greater than 0. So this implies we are taking product of all the positive eigenvalues. So this implies the determinant of Cx must be larger than 0 because product of the positive quantities must be positive. Okay, so these are like if and only if. Also the other way we can prove. Okay, so so I can leave this up to you. This is more about linear algebra now. Okay, but these are the things we have. Okay, so examples of covariance matrices. So consider the two independent random variable x and y, and they follow the uniform 0, 1 distribution, and let the random vectors u and v be defined as this, then are the matrices Cu and Cv positive? Okay, so this is something like you can try to prove. Actually, I don't think there is any trick here. Okay, so what you are supposed to find is prove actually for this example. Okay, but in general we have proved already that the that Cu and Cv are definitely in the general case we have proved, but here the question is about verifying it for yourself. Okay, whether it's positive definite or not. Okay, so I think you can go ahead and try this out. I don't think like I have to do this. Okay, so it seems like a verification of straightforward case, right? X and Y uniform and all these are given to you. So from here you can compute the expectations and variance, uniform distributions, it's known, and so on. Okay. Okay, so as expected, we can also define cross correlation and cross covariance, right? Cross means like now there will be a mix, right? So earlier we were defining Rx. So okay, the correlation, just the plain correlation, and that is expectation of X transpose, right? There is no cross from here, just X with X transpose. So in the cross case, we will just replace one by the other variable on other random vector. Okay, so that will be the same thing. Will be done for the covariance. We had expectation of X, sorry, X minus expectation of X, and then X minus expectation of X transpose. Okay. So substitute one of them by Y. So we define the cross correlation like this and the cross covariance to be like this. Remember, this is now different here. This is now different here. Okay, so but the like usual extension of what we have done in the two variable case. Okay, and we can also define functions of random. Actually, I should say it vector now. So now we can also talk about functions of random vector. Now X is a vector. Okay, so X is some n-dimensional vector. So where we assume that G is continuous, invertible. Okay, so this is about method of transform. Okay, so we can also define that in the general case. So once again, we assume that it's G is invertible and let that inverse function be H. Then X can be solved as H times Y, and this is how X can be solved. And if that is the case, if you are able to solve this, then the PDF of Y, yeah, so we assume that not assume, but we are supposed to find the PDF, right? So we are supposed to find the PDF by using method of transform for PDF of Y. PDF of X is, let us say, is known to us. Then PDF, how can you compute the PDF of Y? And that general definition of the method of transform. It is looking more compact now because we have used the vector notations as HY. Okay, but in fact it is H1 this, H2 this, and so on. So we have used the vector notation, and then we have the determinant. We have the absolute value of the Jacobian. Okay, so Jacobian is given by this, which is the determinant of this guy. Okay, so once again, the main thing is to be able to find the inverse function, and once you are able to find the inverse function, it's rather after that it's just technical things that you are supposed to find these partial derivatives, make a matrix, take a determinant, and plug that value here, and then just find those. Since you are able to find the inverse, you are now able to find the individual components, and then you can just replace those here. So solve for X and then put those values here. That's it. So method of transformation for the random vector case also follows without too much difficulty. So in a very specific case, we can think of an example like this where Y is a random variable which is given by AX plus B. Obviously, X is a random vector and Y's output is also a random vector. So obviously A is fixed and non-random. So this is like a constant. and B is a fixed. B is also a constant. A is a constant. X is a random vector. So that is not a constant. Okay, it's consists of components are random variables there. So find the PDF of y in terms of x, right? So if we want to use the method of transform, then we are supposed to solve for this, right? So now the matter is like whether we can solve for this, and I think in this question we must be assuming that A is invertible, right? So fixed and invertible. Otherwise, I don't think we can do much, right? So we should be able to solve for this. We can solve for x if A is invertible. So that's the easier case, right? So in that case, x will be A inverse y minus b, right? And this will be our hy that we are looking for. And if we use the method of transform, so method of transform told us that fyy will be the PDF of y will be given by the PDF of y will be given by fx hy and then absolute value of the Jacobian, right? So fx yeah. So we are not given anything about x actually, so we have to just keep fx as fx only. And hy we know hy is A inverse y minus b, right? A inverse y minus b, and then the Jacobian. Okay, so we have to take the they take the derivative of h with respect to y and so on. Okay, so I can just keep it depending on. Okay, so we are supposed to like find the derivative of j. Okay, I mean the determinant of this guy. So if I take a derivative of this, right? So do you know the matrix derivative, right? So here we are supposed to find the matrix derivative. So this will be like A inverse. If you take the determinant of A inverse, it will be determinant of A inverse is 1 over determinant of A, right? Okay, so this guy we know. Okay, so this will be, so we can simplify it further, and it's like determinant of A and then fx, because fx we don't know, so we have to just keep it like this, A minus b. Okay, so this is something, this is where we can leave it. So method of transform makes it a bit easier, provided you can find the inverse function, obviously. Okay, and just like before, we can also define jointly normal random variable. So the x1 to xn are jointly normal if the linear combination is also a normal. So we have done this a two variable case, is just extension here. And random vector, so we can also define in terms of a vector, is called a normal vector if the random variables. So a vector will be called a normal vector if the components are jointly normal. Okay, so and consider a random vector z whose the components satisfy the normal and they are IID. In that case, the PDF of z in the vector case will be written like this, because these are again extension of what we have done before. For n equal to 2 case, remember it was just 1 over 2 pi. Okay, but now we can extend this to the general case. Okay, and then for a random vector x with mean m and covariance c, the PDF is defined like this now. Okay, so I will try to derive this in the next class. Okay, just to see why it is like this. Okay. Okay, so I think we can stop here. As usual, like when we go for mean m and covariance c, we start from the standard normal, and then we change the standard normal in such a way that it becomes a mean m and like covariance will be c. Okay, so the derivation will assume, so we will start from the standard normal, and it's possible to go here. Okay, by doing some proper scaling like we did before. Okay, so we will try to do this in the next class. Okay, so I will stop here. Sum of two normal is not necessarily normal, right? So this is something I mentioned and I did not do this. I'm going to put that in the slide itself. Okay, so you can look into that result later on. Okay. Okay then, so I can stop here. Okay, bye. Have a nice day.